Morning, everyone. Let's begin. Your next homework assignment is due on Sunday of next week. And you can see from this next announcement that I'd like you to bring a computer to class next time when we meet. And the reason for that is that we're going to be doing some Excel activities where you'll need to calculate factors using the computer. I'm going to sort of teach you the quick way to do things using Excel. So you don't necessarily have to bring one, but if you work with someone else who brings one, then that'll be acceptable. So at least one person in each group has to have one. So any questions about a computer? Is everybody here either own a computer or have a friend that has one that they can work with here in the classroom? Is that going to be okay? All right. Sometimes tablets have Excel, like there is Microsoft Office for tablets, and that might work, but like an actual laptop is better. But if all you've got is a tablet, bring it along and let's just see how it works. Today we're going to be talking more about interest factors, and specifically, rather than just looking it up from the table, I'm going to show you the formulas that are used to generate those tables. You already know the formula for one of them, I think, maybe two of the columns, but there are some formulas that we can use to calculate all of them. So we're going to get into that. Any questions about the announcements in general? Okay. This figure is taken from the supplied reference manual for the Fundamentals of Engineering exam. They give you an equation book, right? When you go take the test on the computer, the equation book is actually computerized, and so you can search that equation book by keyword. So if you're working on a transportation problem and you want to do like a vertical curve, you could just search by vertical curve. But some of the equations that are in there are related to cost analysis and engineering economy. They have a bunch of different table factors in there, and then they also have these formulas provided. And what you'll notice is that under the symbol column, they're writing things the way that I've sort of been phrasing the problem summary as we've been solving them in class. For example, if you have to find the future amount for some present value, then what you'd use is that top row. They call it a single payment compound amount. I never remember what those labels are supposed to be. I just look for the symbol because it's the most sort of quick way to interpret what's going on. So in the symbol for the first row it says P/F, which means what? Oh, sorry, F/P. I said it backwards. Find the future given the present. So the unknown is first. And in the second column it gives you a little bit of a clue. It says it converts to F given P. And so what you know is going to be in the denominator of this symbol thing, and the unknown is in the numerator. And so then it's got the formula here in the last column, 1 plus I to the n. And you've seen that before. What about the next row? It's saying 1 plus I to the negative n. And that's just because if we had, for the first one, F/P is 1 plus I to the n. Now, if we want to find instead P/F, it's just going to be the inverse of that. So it would be 1 divided by 1 plus I to the n. And another way of expressing this is, 1 plus I to the negative n. So they're just maybe saving themselves some vertical space by saying to the negative n power. There's formulas for all of these. And those tables that we looked at, we had the 8% table, we had the 10% table. If you go to the back of your book or to the FE manual, they have so many different interest rates, but sometimes they won't have maybe the 8.5% interest rate. And that's what you're going to need to look up, is some interest rate that isn't necessarily given in the tables. And so that's where these factors can come in useful. All right, does everyone have a copy of today's in-class exercise? This is in-class exercise number 8. I'd like you to take a look at problem number 1. Of course, as always, it's fine for you to collaborate on this, but I'm just stepping you through a problem to use this table, which I've also copied onto the in-class exercise itself and in the notes. Since it's a bit small on the screen, this last page of the notes is the table as well. So that's easier to read. Take a look at problem 1. Okay, part A asks you to summarize it in that sort of abbreviation language that I've introduced before and is in the FE manual. So what kind of problem is this? This is the kind of problem where they want you to find the present given some future amount. So it says the future amount is $50,000 and that's in 7 years. And what is the present value of that future payment for a discount rate of 8%? By the way, I got a good question. Discount rate. What is that? Is that the same as interest rate? It was a good question. And the answer is yes, it's the same. But sometimes problems like this, if you're going backwards in time, like if you're taking a future amount and you're finding the present, they call it a discount rate because the money is getting smaller. So they call it discounting if you're taking like future earnings and you're trying to find out what it's worth in today's dollars. But don't get too hung up on the language. It's obvious that 8% is the only interest rate that's mentioned in the problem statement. So it's P/F, comma, I equals 8, and then N equals 7. All right. Now write the formula. So we have a variety of formulas to choose from in that last column, and you just find the one for a P/F. So it's 1 plus I to the N. Then in part C, you solve for it, and that's called the factor when you find this 0.5834,904. How many of these numbers should you show? Could we just say 0.6? If we said 0.6, then think about what our answer is going to look like. It would be 50,000 times 0.6. Can anybody do that calculation? What is 50,000 times 0.6? Oh, okay. Nice and easy, right? 0.6 times 50,000 is 30,000. Okay. Now think about how you'd feel if your bank rounded off like that. I guess it depends on if you're getting more or if you're paying more, right? You'd feel great if you're getting more, but if you're paying more, you'd say, well, let's take a few more digits of accuracy. All right? So what you need to do is always keep all of the numbers in your calculator and then multiply by 50,000. It looks like maybe something's happening here on the screen. It's happened before. Okay, there it is. So I've written it here, but in my calculator, I even keep the ones after it. And then I multiply by the 50,000 and 29,174.52. Any questions so far on A through D? All right. Now what I wanted to do is compare that to the table lookup method. And in this case, it's actually, the two answers are pretty close. And I think it's because the table lookup 835, 583, and then 0.4904 is pretty close to 0.5. Sometimes they won't be that close. In this case, we're only off between the equation method and the table lookup method, only off by 48 fils, which is a very minor difference. Sometimes it'll be off by several dirhams. So depending on if I said table lookup or the factor method in the problem statement, either way is okay. Another question I got as I was walking around is, how do you know which one to do? Should you do the table method or should you do the equation method? If you have a table for the right interest rate and the right number of years, then it's fine to use the table, unless the problem says that you have to do the equation method. But the table is usually a nice shortcut, so if you've got one, go ahead and use it. But sometimes you won't have what you need for the table because the the rows go down to maybe 20, and then it says 25, 30, 35. So sometimes you won't be able to use the table method if n equals 33. You know, if it's some odd number of years, or if the interest rate was 8.3%, there's no table you can look up in your book for 8.3%. You'd have to use the equation method for some odd interest rate. All right? Okay. So this is one of those situations where what if you didn't have a table factor for an interest rate in the problem? You probably remember interpolation. And what this slide is showing is that if you had a problem where you're finding the future amount for a present value, so this is compounding rather than discounting, the factor is going to be greater than 1, which means the future amount is bigger than the present amount. So f/p for 8.3% and n equals 10 years. Well, there is no 8.3 table in the book or in the FE equation manual. So you could either use the formula method, or next time when we get together in class, we're going to use Excel, and there's a function in there that's just equals FV. It's a magical function. There's lots of magical functions in Excel that makes things so easy for you. And you're going to love what it can do. And you're going to wish you maybe started looking at Excel earlier when you see how nice it is. So you could get the factor either way through the formula or spreadsheet. But let's say that you're stubborn and you just want to do the interpolation method, use the tables. So interpolation is sort of finding what is between those two. And so let me draw a graphical representation of what the interpolation solution is looking like. All right, so what we could do is have, here is the interest rate, and over here is 8%, and over here is 9%. And then for 8%, maybe our factor, if we know from the table, the 8% factor is 2.1589. So 2.1589. And then the 9% is going to be, as it says from the table, 2.3674. Okay, so we have this and that. So if it was 8.5, that would be easy. We just average the two, right? But it's not. It's 8.3. So 8.3. Anybody have an idea of what you're going to do? Yeah. Yes. Okay, so you find the difference. So you have the change in the factor. Now what? Change in interest. And then we've got the slope of the line. Very good. Then what's the next step after that? Okay. So 0.3 times the slope plus whatever was at 8%. Okay, so do that on your paper. That's part 2 of the in-class exercise. On the board, it was showing like the graphical representation. So the question is, what's the factor at 8.3%? We say, well, it's going to be more than whatever it was at 8. but it won't be as big as it is at 9. It's somewhere between the two. You know, how much between the two depends on the slope of the line. So the factor for 8.3% equals the 8% factor plus 0.3 times the slope. Why am I doing this part, the 0.3 times the slope? Yeah, that's the extra amount over 8. So we know that it's 0.3 down here on the x-axis. Multiplying it by the slope tells us vertically how much that 0.3 turns into. It was 0.3 extra here, and then the slope, which is, as it says on the screen there, there's 0.2085 increase in factor for every full percent. We don't have a full percent. We only have 0.3 of a percent. So we have 0.3 times the slope, and then add it to the amount of the factor for 8%. Now this one didn't ask us actually to find for any dollar value or amount of dirhams. It was just saying to find the factor. Yes? Good point. Yeah, we are assuming a linear curve, but it isn't linear. And you'll see from this note that if you solve it by the equation, the true answer is 2.2197. And so that differs from this interpolation. This is accurate. The equation method is accurate. Interpolating through the table is only an approximation. And let's see. Well, this shows the solution. The reason why is that it's not really a line between the 2 points. It's more like it's a curve that we are approximating as a line. So it's acceptable for a quick estimate, but for true accuracy, you should always use the equations. Good point. So are there other questions on this second in-class exercise problem? The last thing that we're going to talk about today are called gradients. And so let me show you the form of a gradient. In a gradient, it's increasing by the same amount every year that the gradient is being applied. So we start with year 0, and nothing happens in year 0. And then in year 1, it's 0g. So g is whatever that amount that it's increasing by every year. So in the first year, year 1, it's 0g. Then in year 2, it's g. Year 3, it's 2g, and so on. Now the gradient could be an inflow, or it could be an outflow. Here, the gradient is being represented as an outflow. So the interpretation of this graph here is that you got some money in year 0, and in year 1, you didn't have to pay anything back. But then in year 2, you had to pay back, let's say, for example, 1,000 dirhams. In year 3, you had to pay back 2,000 dirhams. In year 4, you had to pay back 3,000 dirhams. And so this is a very difficult loan, right? If every year you have to pay back and it keeps growing and growing. So gradients are a little bit unusual, but we can deal with them anyway. So just to get a first taste of gradients, I'd like you to look at this problem where in year 0, there's nothing that's shown there. We want to find out in the first step, what is the present value of this gradient? So in year 0, there's nothing. In year 1, there's nothing. But then you receive 200 in year 2. You receive 400 in year 3. And then you get 600 in year 4. So you're getting all this money, but it's in the future. What's the present value of this cash flow if it's 8% interest? Now, you probably already know that you could, if you wanted to do it the long way, you could take the 200 to 0, then separately take the 400 to 0, and then take the 600 to 0. So you could do it like 3 different versions of P/F. But don't do it that way. In this case, in the problem statement on problem 3, you'll be able to use the table lookup for part A. Then you'll have to use the equation method for part B, because there's no factor for the second part of the problem that you're going to need. Yeah. What we're saying is, okay, so someone will pay you that, or in year 4 they'll pay you that, and it's equal. It's like you can either take this or take this as it's shown, or take this amount in year 4, and it's numerically equal.
So there is no gradient in the last year.
Right. Right. So we're saying either, take the gradient, or for the first part, take it all now, or in part B, take it all in the future. But there's no gradient. It's just transferring. It's sort of like converting it. Yeah. Let me draw something on the board here just to illustrate what we've done in this problem. Okay, what was given was a gradient where it went 200, 400, 600. So 200, 400, 600. Now this problem is sort of like if someone came to you and said, I'll pay you this money. This is what I'm willing to pay you. In year 2, you get 200. In year 3, I'll give you 400. And then in year 4, I'll give you 600. And just what if the typical interest rate in this situation was 8%. Like that's what the banks were paying, or that's what it costs to borrow money, or that's inflation. Let's just say all of those things are equal. The general interest rate in the environment is 8%. What if you didn't want to wait that long? What if you wanted all the money now? What that person should pay you, instead of the gradient, they should pay you how much now is the first part that you found. So you found what was the present equivalent of that cash flow. So the 930.02, it's equal to the gradient in present dollars, in today's money. Now in part B, what if you're the kind of person that is very patient? And you say, no, I don't want it, this is silly, to give me a little amount and then a little more and then a little more. Let's just make it all of it in the future. I'm a patient person, just giving me all of it in year 4. So what we did in part B is you convert the cash flow diagram into a future value in year 4. So that's maybe just one way to think of what this graph is representing. Do you have any questions about the solution? So this equation looks nasty, but it wasn't so bad, right? We can handle it when we need to. All right, let's take one last look at these announcements and remind ourselves of what's in the future. You're working on homework number 4. How many of you solved half of homework 4 before lunch like I suggested you should? All right, so it was possible after all. After I said that, I wanted to make sure it wasn't some false dream I gave you. Those are really quick problems. They don't take too long. So if you haven't solved it already, I bet you can do a lot more now that we've done a little bit of gradients. Bring the computer to class next time, and Excel will definitely make it worth your effort. You'll learn a lot from Excel. Question? What's that? Bring it to class next time. So bring it, what did I say? Thursday. Bring it Thursday. Yeah, today's Tuesday. Yeah, I think maybe I'll have you bring it next week as well, but bring it next time. Do you have a question? Because it's gaining interest into the future. All right, I'll see you next time. Have a good day.